Thank you for coming, and I'm gonna tell you about TimescaleDB, which is a new time series database, and we are, an open source project. We have a page on GitHub. We are licensed under Apache 2.0, and we are packaged as a Postgres extension. We've open sourced about 5 months ago, and we have had a lot of growth and interest since then. So we have a vibrant community around us, an active Slack group, a lot of people submitting issues. So, we invite all of you to join us and help us develop the product. But the reason we started developing this product is because time series data is everywhere. A lot of you are probably familiar with time series data coming from computer systems and data centers. Being in New York, the original use of a time series database was financial and market data, but now we're seeing new industries start to use time series data more. Industrial spaces are starting to use time series data for predictive analytics. Transportation and logistics use time series data to move and ship products around more effectively. And the reason that time series data is becoming more and more prevalent is because it's very powerful. Using past data, we can build a historical. So using past data, we can build historical models and use that to monitor what's happening today and what's going to happen in the future. So what is time series data? Well, time series data is data that is kind of coming in from sensors or everywhere constantly over time. It's characterized by high velocity, is coming in quickly, as well as high volume. And when I say high volume, I really do mean high volume. IDC predicts that in the year 2020, we're going to have 44 zettabytes of this type of data from IoT sensors alone. And don't worry, I had to look up what a zettabyte is as well. It's 1 million petabytes. So it's really a lot of data. Today, people are storing this type of data and processing it and analyzing it mainly in two different types of systems. One is a traditional relational database, and one is a NoSQL database, where about 70% of people use NoSQL and about 30% use relational databases. This is data from a Pocona survey in February of this year. And let me go through both of these types of systems kind of one by one and tell you what we see as the challenges and opportunities with each type of system. So first, let's go over relational databases. You can imagine that time series data could just be put in a relational database where you just have a regular table with a time column, and that's it, you're done. You just insert data to that table. And, go back. Let's try that. I'm actually going to do what you should never do in the presentation, which is a live demo. So I'm going to start inserting data. You actually don't need to read it for now. I'm going to have it just run throughout the talk. And the important part I'll show you when I'm done at the end of the talk. But right here, up here, I'm inserting data into plain Postgres in the way I described. And on the bottom, I'm inserting data into TimescaleDB, and the benchmark is reporting how many rows a second I'm inserting. So we're going to let this run throughout the talk and check in with it at the end. So now we're doing a demo, but we did this ahead of time, just like a cooking show. I'm going to give you the results right now. So this is inserting data into plain Postgres. On the y-axis is the insert rate in terms of rows a second, and on the y-axis is the data set size you're inserting. And you can see that as the data size grows, after a certain point, the performance falls off a cliff. And it falls off a cliff not only in terms of the average that you see, but also in terms of the variance. And what's actually happening here, the difference between here and there, is that your indexes no longer fit in memory. And once your indexes no longer fit in memory, inserts become really chaotic in this way. And let me explain to you why with a simple illustration. So if you guys remember computer science, kind of the early years, this is a B tree, which is a data structure that holds the data kind of in order. And this is a regular B tree, and I'm going to insert the numbers 5, 17, and 8 into the B tree. So now I'm inserting the number 5. To insert the number 5, first you got to find the leaf node of the B tree into which you're going to insert the number. That means you got to go from the root of the tree to the leaf where that number will live. In this case, this requires two reads. You got to read the root of the tree as well as the left node. Now, I told you that bad things happen when the B tree can't fit in memory. So in this example, I'm going to pretend that my memory capacity is 2 of these nodes. So when I insert the next number, which is 17, I need to insert it into the center leaf. But now I already have 2 leaves in memory, which means one of the leaves in memory I got to write back out to disk. Then I got to read the center leaf in and insert the number 17 into the center leaf. You insert it in memory just into the leaf. But now when I insert the number 8, then I got to do the same thing again. I got to write out the center one, and I got to read in the other leaf node. So I just inserted 3 numbers, and that required 6 IOP operations, 4 reads and 2 writes. So this is a lot of I/O contention for such an easy operation. And if you imagine a bigger tree, you can imagine a Christmas tree with blinking red and green lights. And the only present you're going to get is a lot of I/O contention and bad performance. So that's the basic challenge with this kind of data structure. And I would just like to note that I/O amplification makes this worse, because every read and write of a node is 8 kilobytes, even though your data changes might be much smaller. So not only are you having a lot of IOPS, you're having a lot of throughput as well on your disk. So you might say, okay, relational databases are not good for this type of data. Why don't we use NoSQL databases? And NoSQL databases were actually designed for a similar type of thing. All of these NoSQL databases, Cassandra, Influx, Mongo, they kind of took advantage of this data structure called a log structured merge tree. And the idea was there that instead of inserting data into random parts of memory, you would batch up all the data you're inserting and insert it in one big chunk at a time. So let me go into a little bit more detail. A LSM consists of a mem table, which always lives in memory, and a bunch of SS tables that are old mem tables that have been sorted and written to disk. So each of these, both mem tables and SS tables are just lists of data which are sorted. So when you insert data, you simply kind of append all of this data into your mem table. And after your mem table gets full or gets too old, then you sort the data in the mem table and you write it out to disk. Now this works great for key value stores because you have a simple, no, go back. You have a simple stopping criteria when you read the data back. Imagine one of these numbers is the keys. So let me back up a second. I want you to notice one thing. The number 5, which is the key here, shows up in all 3 lists. So you no longer have a global sort ordering of your data. You have some kind of cascading ordering, right? So if you are reading the number 5 as a key, what you can do is I'm going to read the SS table as an order, and when I reach the first SS table that has a 5, I stop. I'm done. I found it. Unlike discrete keys, time is not discrete, it's continuous. So it's much harder to come up with a good stopping criteria for when you can stop reading the additional SS tables. And a lot of the NoSQL time series databases have to build a lot of like ancillary data structures to deal with this problem. And the problem is all of these ancillary things have to live in memory. And so what you get is a lot of these time series NoSQL databases have a large memory footprint. And something you guys might have heard of, because of that, they have problems dealing with high cardinality data sets. Because the greater the cardinality of your data set, the more these ancillary data structures, the more memory they require. So that's not the only problem with this approach. Also with LSMs, you don't get to have secondary indexes. And you have poor support for out-of-order data. To give you a feeling of why, if you have out-of-order data, now your data is more spread along those SS tables. It's not kind of clustered into the most recent SS table. In addition to this, you have all of the drawbacks of giving up SQL. Namely, your analysts have to learn a new language. You lose all of your familiar tooling and visualization tools that speak SQL, and you lose joins. And let me harp on this for a moment, because I think for IoT data, joins are very important. So imagine you have a sensor that has, temperature, humidity, and free mem going to you. You might also have associated metadata giving you information about your device. Something like customer ID or the location, if the location doesn't change often, right? And if you don't have joins, that means in order to analyze this data, you have to perform joins at the application level with all of the additional complexity that involves. And even worse, your data may be out of sync. Remember, you're backing up these 2 databases differently. So when you restore it, you lose consistency. What a lot of people do is, for these type of systems, is they denormalize the data. So they take the metadata and put it in along with your time series data. Now, this has two obvious problems. One of these problems is that the data volume blows up because you're writing additional info with each row. And then what happens when you need to update the metadata? Either you have to have some kind of special handling in your application logic, or you have to go through and update all the old rows, which is very expensive. So we asked ourselves, is there a better way? Can we have a relational database scale with time series data without incurring all of these negative effects of NoSQL? And surprise, surprise, I'm going to tell you yes, because if I told you no, this would be a very boring talk. So we actually built the system. It's called TimescaleDB. It's an extension on top of Postgres, which is a kind of a well-known relational database system. And right now I'm going to tell you how. And the how is pretty much we looked at the data and we saw that time series data has certain characteristics that are different than the OLTP characteristics a regular relational database was built for. So if you think of a regular relational database, the canonical example is a banking system where you have accounts where you credit one account, you debit one account, you put it in the transaction, etc. And if we think of that, then you're right, then you do primarily updates because you are updating the account balance of each account. And your writes are randomly distributed because you're kind of random, your primary key is the account ID, and you're accessing kind of random accounts to credit them and to debit them. And also your transactions are also randomly distributed along your tables. As I said before, in contrast, time series data is different. It's primarily inserts and primarily to the most recent time interval. So in this talk, I'm going to tell you about time series data, but if you have OLTP data, please stick around because Cockroach is going to tell you about exciting improvements in the OLTP space. So, don't leave. So let me give you a picture again of this time series data that we had. And time series data is something you can partition. And the most obvious way to partition the data is you can partition it by time. Break it up into time slices. And because this data often comes from diverse sources, you can also usually partition it by another dimension. In this example, I'm going to use dimension ID, but I'm going to call it space for generality. So what we do is that we partition our data into time and one or more other dimensions. And we call each kind of subpartition a chunk. And a chunk is actually a table in Postgres. I'm going to go into that a bit later. So the chunk is the particular partition, and we call all of the data now a hypertable because it's partitioned across many dimensions. The interface that a user sees is the illusion of a hypertable as a single table. So all your selects can go across your hypertable and your inserts as well. So you insert to the hypertable, and underneath the hood, it routes it to the correct chunk. Now, why is this useful? It's useful because the indexes are local to chunks and not to the hypertable. So if you can imagine that you're writing only to a small set of chunks, namely the most recent chunks as partitioned by time, your indexes are going to be a lot smaller. And your whole goal in this game, if you will, is to make sure that the indexes are small enough to fit in memory. So you adjust the chunk size for that goal. And there are many ways to partition by time. I'm gonna give you a couple of strawmen and then our solution, so you can partition by a fixed duration, say a day. And this works pretty well until your data starts growing. Once your data starts growing, your chunk used to be, 2 gigs. Now your data volume has increased. Your chunks are 4 gigs in size. They no longer fit in memory. You're back to square one. So you might say, aha, so what I really need to do is I need to partition by chunk size. And one of the ways I can do this is I can say, when inserting into a chunk, I'm going to check whether the chunk is too big. And if it's too big, I start a new chunk. And if it's not too big, I just expand the chunk to include that time period. Well, this doesn't work for late data, because you might have data kind of arriving on the edges of your chunk, say on day 1 and day 3, and much later where you have the stuff in the middle. So you might have already created a chunk that spans 2 days, and now you're stuck. You have to fill it up, and if it's too big, it's too big, and it won't fit in memory anymore. So instead, the approach we do is more like the first one, where we say when we create a chunk that it's a fixed amount of time. But over time, as your data volume grows, you can change what that interval is for new chunks. And so you might start off saying that a chunk is 1 day, 1 day long, and then as your data volumes grow, you can change that and say new chunks are going to be half a day or 6 hours or whatever. And this solves the late data problem, because the order of the data doesn't matter anymore, since you're only creating data for a particular time period, and you can't make them too long. Now, right now, you adjust this chunk duration manually in our system. Starting with the next release, we're gonna put in a adaptive algorithm, which is gonna look at your previous chunks and kind of use a moving average to adjust it for you. Actually, once we started doing this, the original reason we did this is to solve the insert problem. But once we did this, we found that there's a lot of benefit actually to partitioning your data in this way. So I already outlined the first benefit. Another benefit is data retention. Often, especially with time series data, you do things like, say, keep my data for 3 months. And once my data gets older than 3 months, delete it. Now, if you don't do partitioning, that means you have to do a delete operation, which is a row by row deletion, right? And this is both slow, because you have to scan all of your rows and mark them as deletions. And as anybody who has dealt with ODBMS knows, vacuuming is a problem, which is kind of the process that goes in and cleans up your tables after deletion. So instead of doing that, if your data is partitioned by time, what you can say is just drop the chunks that where all of the data is older than 3 months, right? And dropping a chunk in Postgres corresponds to dropping a table, which physically on the file system is just a deletion of a file. So it's very fast, and you don't have any vacuuming, and it's much more efficient. Another benefit now is that now you can spread these chunks across disks, which allows you to have a lot of I/O parallelism, as well as kind of elastic expansion of your data size. Because now you could add disks, and you could say, oh, just put the new chunks onto new disks. Notice there's no data movement here. You're just telling it where to put new chunks. And if you kind of squint at this, you could say, well, instead of distributing the chunks onto multiple disks, I could, using the same technique, put these chunks onto multiple nodes. And now I have clustering. And this is actually the technique we are using, and it's in active development, but our clustering solution is not yet public. So right now, you can add more disks easily, but you can't add nodes. Okay, on the query side, you also have optimizations you can do, because if your query involves where clauses on your partitioned columns, you can now exclude chunks from your queries and not even touch them during the query. So if I'm partitioning by device ID and I have a particular device ID in my where clause, I can just look at those chunks that belong to that device ID and no other. And I can do kind of the same trick on time, which is my other partitioning dimension. And I can do that using a constant time or using, math based on time. And even though this kind of constraint exclusion is a feature that's built into Postgres, when it comes to time, native Postgres is not powerful enough to exclude things when you do kind of math on it, because the time zone issues, etc. We fix this, but we allow you to do proper constraint exclusion. And actually, even by space, Postgres doesn't really do what you want, because we want to use hash partitioning, and constraint exclusion in Postgres doesn't work with the hash partitioning, but in our system it does. So kind of, let me give you a high-level summary of the differences between Timescale and plain Postgres. We improve insert performance, and we improve insert performance by doing partitioning. We do this automatically for you, so the user doesn't have to think about it. We add some functions for time-based analysis. I'm not going to go into them in this talk. You can ask me offline. We do time-aware query optimizations, some of which I showed you before, and we do much faster deletes. The differences from a NoSQL database is, I think the most important is that we support secondary indexes. We have much lower memory requirements, and we don't have any problems with high cardinality. We also allow you to unsilo your data. So now you can contain metadata as regular Postgres tables alongside your time series tables, and you can do proper joins across them, and you get all of the power of SQL. Let me quickly go over some benchmarks. This is the graph I showed you before with Postgres kind of falling off the cliff. In contrast, we have pretty high insert performance along with, constant insert performance as the data set size grows, and actual numbers for one row insert at a time. We support about 14,000 rows a second. In this benchmark, we have 10 metrics a second, so this translates to 144,000 metrics a second. If you batch your data inserts more, if I'm inserting 10,000 rows in one batch, then my performance grows to over 100,000 inserts a second with over 1 million metrics a second. Next. So in terms of query performance, I'm not going to give you exact queries because, as we all know, all of our query patterns are very different. I'm just going to try to give you kind of gut feelings for how our query performance changes. If you do simple table scans and column rollups, there's not much improvement. But if you are doing group bys, you get significant improvement. Here, constraint exclusion really helps. If you do group bys with limits, which are very kind of natural things to do, say, give me the average CPU load by 5-minute intervals for the most recent 5 periods, then because we're building into the optimizer a lot more knowledge about the nature of time, we're able to get, stupidly high performance. And also delete much faster, as I mentioned. But we're not fast on everything. If you're doing really low latency key value type lookups over your data, then we might be slower because we're not partitioning data, and so there's a lot of chunks, and so the planner kind of has to work harder, which adds a few milliseconds of extra latency for planning time. And so if you are doing really low latency queries, we might not be appropriate, but this is not the kind of queries we see over time series data. Usually people are trying to aggregate the data or operate over some kind of longer time periods. And so this planning penalty really is overshadowed by the other benefits usually. Our interface is your familiar SQL interface. So you would create a table using a regular SQL create table command. You would run one of our functions to transform a regular table into a hypertable. And after that, you can do all of your regular SQL commands directly onto the table. In this case, I'm just copying data from an old table into the new hypertable. But you can do selects, you can do updates, all of these things just work. You can do upsets, for example. Yeah, let's see how our live test is doing.
We got time. Let's hurry it up.
If I can find it.
There it is, it's on.
Yeah, so so if you remember, I said the top window was Postgres, the bottom window was TimescaleDB, and I'm just gonna read it. I'm just gonna read off these numbers. The row rate for the most recent period on Postgres is about 18,000 rows a second, while for Timescale it's about 86,000 inserts a second. And the total over this period for Postgres is 56,000 inserts a second, and for Timescale it's about 109,000 inserts a second. So when I said that performance drops off a cliff for Postgres, it happens pretty quickly. I've been speaking for 40 minutes. In 40 minutes, if I saturate the pipe you're already seeing a major performance difference.
Let's speed it up. Play it.
Okay, so again, this is kind of the closing of our talk. We are an open source project available on GitHub. We have a few blog posts that are very technical. If you want more information, you could read our blog, or you could, our CTO did a podcast with Arye, if you prefer listening to this sort of stuff. Yeah, and thank you.
So we're now open for Q&A. If you have any questions, here's your turn.
2 questions, so cockroach can have.
All right, my question was for the types of queries it's optimized around. You said it's good for group bys with a time series data. How does it compare to things like Redshift or BigQuery that also allow you to distribute it against a time period but are columnar oriented?
Yeah, so
Just take
there are a couple of things to say. First of all, things like Redshift, you don't get secondary indexes, so they're only good for these kind of large group bys and not for anything else. The other thing is to say that since they're column-oriented, if you're doing a group by where you are aggregating one metric, they're great. But if you're aggregating 5 metrics over the same time period, then it has to now hit 5 columns, and you have a significant penalty there. So again, for simple roll-ups, they might be better, but if you are getting to anything more complex, then we're competitive or better, and we need more information about your load to tell you exactly.
Also talk much more details than we're talking about. Okay.
I was wondering if you could tell us a little more about how deletes are sped up so much. Is it like a context-aware where if I write a delete that only accesses a certain chunk, that can be done faster?
Matt.
So let me. The deletes I'm talking about are deletes of old data. So 1 second. Yeah. So as I mentioned, data is partitioned by time. So if you are deleting old data, like old data below this line, they fall into separate partitions. So you can just drop the entire partition without going through it row by row. So a drop of one of these partitions is simply a delete of a file off the file system. So that's really quick. Does that make sense?
I have 3 questions, if I may. First one is, it's great that your stuff is a Postgres extension. RDS does not probably let you install the extension. Is there a way that I can hack it into RDS? That's the first question. Can I continue, or you want to address it? Okay. The second question is, I'm really happy that you did something about the time arithmetics, because we're dealing with table partitioning, and when you put the absolute date in the query planner works. If you put arithmetics, it doesn't. It relies to indexes. So please contribute to Postgres if you can. That's not over. I mean, the question is, are you planning to contribute? And it's a request. The third question is about secondary indexes. Since you're dealing with table partitioning Postgres, I think, Postgres cannot help you with secondary indexes. How are you doing secondary index? Are you doing some merging of indexes? I mean, whatever you can tell us.
So firstly, really quickly, actually, so RDS whitelists certain extensions. We are not one of those extensions yet, but we are working with them. I'll get your email address. There's actually a form you can fill out to request it, and obviously the more people that request it, the more likely it'll be whitelisted. But it's just a matter of time because we're Apache 2. It's yeah. Yeah, our users are on AWS, they're on Google, they're on Azure, they're on their own clouds, they're on their own boxes at the edge, they're maybe on feature something else. So we're happy to support them wherever they are. Yeah, and we're working with the cloud providers. Second question is about contributing back to Postgres. We're very friendly with the Postgres community. I think there's some quote by Bruce Baumgen over the weekend that was talking about how he's excited about the work we're doing, how it shows the potential in the future of Postgres. We hosted the Postgres US Mini here last Thursday, where we spoke with 2 speakers from the Postgres community, 2 other speakers. We're working with them to get things into mainline, but it's a very slow process for Postgres. It's such a large project to be very careful. So, wherever we can, we will contribute back. But I think just because they're just a larger project, it'll be slower for them. But it's not us. And third question.
Let me just add to that. There's a bunch of kind of special optimizations relating to time that we do that I'm not exactly positive or really appropriate for Postgres, just because they add a lot of complexity which most people will never use. So that's another thing where it's kind of iffy whether it's even appropriate and whether it would be accepted, if that makes any sense. Secondary indexes, yes. So what you can, so it's true that Postgres does not allow, when you create an index on the parent table, it does not propagate to the child tables. But it turns out that you can create your own indexes on the child tables. And if you are able to kind of translate the semantics of the index on the parent table and the child tables, you can create it on the child tables, and it will give you the equivalent speed up, if you will, which is what we do. So we create, there's no global index, but each chunk has its own set of indexes which creates the same effect. We do have a little bit of, like, you have to structure your index correctly if it's a unique index, but other than that one case, this is a general system.
What kind of indexes does it support?
Does it or doesn't?
Does it?
All kinds of indexes. B trees, hash, gen. The only kind of limitation we have is on some form of unique indexes.
Thank you.